All right, we're going to start learning how to write the names of cations, and then we'll work our way to anions, and then we're going to learn how to write the names, ultimately, of compounds that contain cations and anions. And a lot of your Chapter 3 homework questions you will be able to go do once you watch this video, because a lot of them have you name compounds. So, writing the names of cations. Well, it depends if your cation is a main group cation or a transition metal cation. We will name them differently. So if it is a main group cation, which would either be main group 1, 2, or 3, so you see an example from each of those groups here, all you do is, it's really simple. You just name the element and then you add the word ion. So if you have K+, which is potassium, you'd call that you'd write the name of it potassium ion. All right. If we had barium, Ba2+, it would be the barium ion. Okay, aluminum cation, we just say the aluminum ion. So you just name the element, add the word ion. Okay, transition metal cations kind of hits on what I mentioned in the previous video when we were talking about transition metals, with the use of Roman numerals. Okay, so there used to be an old naming system, and just for time's sake, I'm not going to get into that old naming system. But I do want to look at an example here with chromium. Chromium is Cr, and so if you have a transition metal and it can form different charges, here we've got the +2 and we've got the +3 version. You just name the element, okay, so you write the word chromium, and then you put the Roman numerals to indicate what the charge is. So if it's a +2, you're going to put 2 Roman numerals, and then you add the word ion, okay? Over here, because this one is a +3, they wrote 3 Roman numerals, and yes, you always put them in parentheses, okay? These parentheses are important. You always put the Roman numerals in parentheses. So you name the element, you write the charge of that cation on that transition metal in as Roman numerals in parentheses, and then you write the word ion. So if you need to go brush up on your Roman numerals, like for example, if we had a +4 cation, you'd write the name of that element and then you write parentheses 4, okay? And then you write the word ion, all right, depending on what the element is. Okay, so that's how you name cations. All right, let's go to anions. So how do you name anions? Remember, anions are ions with a negative charge. They are atoms that have gained electrons. And so here's several common anions. So let's look at just the first one. If we have bromine, and it becomes an anion, the symbol would be Br with a -1 charge, because bromine is main group 7, so it would gain 1 valence electron to fill its outer shell and have 8. So it would just be a -1 would be the charge. And the way we name this now is we don't just call it bromine anymore. It's kind of a subtlety, but we take the name ending of INE and we change it to IDE. Okay, so instead of bromine, it's going to become bromide. All right, so we change the name ending to IDE. So you could think of it as change the ending to IDE. All right, so bromine becomes bromide. Same idea with chlorine. When it's an anion with a -1 charge, it becomes the chloride ion. All right. Let's look at like oxygen. Okay. Oxygen would become an anion with a -2 charge because it's in main group 6. So it has 6 valence electrons. It wants to gain 2 more to have a full set of 8 in its outer shell. So when it does, we have an imbalance there of a -2. And we would change the name ending from oxygen to oxide. All right. And then sulfur is right beneath oxygen, so main group 6 as well. It forms the S with a -2 anion, and so we would call that the sulfide ion. So that IDE ending lets you know that you're dealing with an anion when you see that, okay? We don't use IDE on cations, just on anions. All right, so that's cations and anions. That's just the rules for the ions. And now I want to switch over to polyatomic ions. All right, this is a table in Chapter 3 of the textbook, so I encourage you to go look at that and maybe even read about them. But this is a table of some, so this is not an all-inclusive table, but it does include several. So there are other polyatomic ions that are not on this table, but a polyatomic, I want to break down this word for a second. Poly means many. Atomic obviously means atom, so we're dealing with an ion here that has more than one kind of atom in it. which is unique. So far, when we've been talking about cations and anions, it's just for an individual atom or one kind of atom, one particular element that we're talking about. But these kinds of ions have multiple atoms of different elements joined together into one ion, one overall big ion. And so that's kind of unique. For example, if we look at this very first one, hydronium, you've got 3 hydrogens and an oxygen all put together, and there's a plus charge on it, making it an ion. And so that's why this is called a polyatomic ion. So when you see something with a charge on it and there's more than one kind of element in it, that's a polyatomic. Okay? Now, of this whole table, there are 11 of them that I want you to know. I want you to memorize. So there's 11 polyatomic ions that I want you to memorize, and they are boxed in red here. And you need to know them for exam 1. And this is just straight rote memorization. The easiest way to do this is to make flashcards or literally get out a blank sheet of paper and see if you can write them all down. Both the formula and the name of that formula. And when you know the formula, you know all the elements, any subscripts that are included, and the charge. Okay? So all parts of the formula are important to know. And then you need to know the name of those formulas as well. Okay, so know hydronium, ammonium, acetate, anything boxed in red. Okay, so take a minute and pause this video if you need to. Make sure you write these down, circle them on your lecture notes, whatever. Have these memorized for exam 1, all right? They'll also be very helpful to memorize them for your homework 3. Okay, so now let's get into writing not just ions now, but compounds, okay? Now remember, a compound is when you join together multiple elements. We're no longer dealing with just a unique element, but instead a compound. And ionic compounds, specifically ionic compounds, generally form between a metal and a nonmetal. All right, so for example, potassium, K, is a metal here, and fluorine is a nonmetal. And when we have them in their ion forms, we got K plus and F minus. They join together to form KF, potassium fluoride. And then calcium would be our metal, oxygen would be our nonmetal. These two come together to form an ionic compound, calcium oxide. Now, how does this happen? Well, one, you need to be comfortable with knowing the charges on these elements now. Based on what main group they're in, based on knowing the octet rule, you should be able to look at elements such as potassium and calcium and know now, oh, potassium is going to be +1, calcium is going to be a +2. And fluorine and oxygen are also main group elements, so I would expect you to know the charges on them now. But let's look at their electron dot symbols. Maybe it'll help break down what's happening and how these join together to form elements. So potassium is main group 1, and you see it's one red valence electron, one red dot on potassium on K. And then fluorine is main group 7, and so because of that you see 7 dots around fluorine right here. And remember, everybody wants a full 8 in their valence shelf, a full 8 electrons. And so fluorine would really like to get one more electron if somebody would donate an electron. And potassium has one valence electron that it would really, really, really like to get rid of. So that's perfect, right, for both of them. Potassium wants to get rid of this valence, and fluorine is like so happy to get it. So when that transaction happens, that's where you get the ionic bond from. And then we represent these guys in their ionic forms on the other side. Now, again, when you go about writing ions, you don't have to include all these dots, but maybe it will help you see, oh, fluorine now has a full set of 8, and the one red one that it gained from potassium is what gives it the negative charge. It gained 1 electron, so it has a -1 charge overall. Okay, let's look at calcium and oxygen. Maybe this, looking at another example, will continue to help here. Calcium is main group 2, so you see it's 1, 2 valence electrons represented in the electron dot structure. Oxygen is main group 6, so you see it's 6 valence electrons. So calcium would like to get rid of 2 electrons to become stable. Okay, it has a full set of 8 underneath. And so if it can just get rid of those outer 2, it's going to be more stable. Oxygen has 6 valence, so to get 8, it just needs 2 more. So if anybody would give up 2 valence electrons, oxygen would love it. Calcium's like, hey, that's great for me. And so both of these electrons, okay, are going to go to oxygen. And then you see that forms kind of represented over here with how the dots are rearranged around oxygen. Now both of the red ones that were on calcium are on oxygen, and because calcium gave up 2 electrons, it now has a +2 charge overall. Okay, and again, if what I'm saying here, as far as you're like, how did calcium get a +2? I don't understand. It gave up 2 electrons. Why does that mean it has a +2? Go back and review my previous video, or go back and review the first half of your lecture notes from ionic compounds, especially where I talk about the octet rule. This is a main group element, okay? So that should help you know why these main group elements, what their charges are going to be. And then when oxygen gains 2 valence electrons, it ends up with a -2 charge overall, okay? So that's kind of what's going on as far as electrons are being traded, and that's how these charges are generated. And now we're kind of transitioning our way into forming compounds between our cations and anions. So this slide, by the way, was really nice because you may have noticed that the cation and the anion have the same charge, like as far as magnitude, like a +1 and a -1. Same for calcium and oxygen. Calcium has a +2, oxygen is going to end up with a -2. But that's not always going to be the case. So what happens, how do we write compounds when you have a cation that is like a +1 and an anion that is a -2? Okay, how would we write the compound for that? Well, if you're thinking about valence electrons and those things being traded, potassium's happy to give up its 1 valence, but oxygen is not satisfied with just receiving 1, right? We said oxygen wants to gain 2 valence electrons, okay, so that it has a full 8 in its outer shell. If it just gains 1, then it would only have 7, and it's not satisfied with only 7. So what could we do so that oxygen gets a full 8 here, and we could form a compound between potassium and oxygen? The only thing we can do, potassium does not want to give up another valence electron. So it's like, sorry, I only have 1 to give you. But if we had another potassium, like a whole nother potassium atom that has another valence electron, it would be pretty pumped to give up its 1 valence electron. So if we had 2 potassium atoms, both ready to give up 1 valence electron, then oxygen would be satisfied because it would be gaining 2. It's just that those 2 electrons are coming from different atoms. Now, same element, but we have 2 potassium atoms here that are both giving up 1 electron. And so the way we represent that when we write a compound is because all 3 of these atoms are going to be involved in our compound, we have to represent that like this. We'll have 2 potassiums, so we'd write a subscript of 2, 1 oxygen. So you'd get K2O would be the compound here. Okay. Essentially, I guess I should write this. We would end up with 2 potassium cations and 1 oxygen anion that would have a -2 charge. Okay. Now the way we represent that as a compound is what I just wrote, K2O. We don't have to write all the charges in when you write the compounds. I'll get to those rules in a minute. But that is how it works with different atoms that are willing to give up or need to receive different amounts or varying amounts of valence electrons. Okay, let's look at calcium and chlorine. Calcium wants to give up 2 valence electrons. Calcium main group 2, so it has to give up both valence electrons. Chlorine only wants to receive 1. Okay, if you look at chlorine, it already has 1, 2, 3, 4, 5, 6, 7. Okay, so chlorine already has 7 valence electrons, and it only wants to receive 1 more to have a full set of 8. So once it gets 1 from calcium, there's not room for another one. But calcium's like, I have to give up both of these to become stable. So the way this works is kind of opposite of what we did here with the potassium and the oxygen. If we had another chlorine atom, okay, so like a whole second, what happened? A whole second chlorine atom that has also 7 valence electrons. Now, one of these valence electrons can go to that chlorine, the other from calcium can go to this chlorine, then everybody's satisfied. Everybody will have either a full octet, a full octet and be stable. So the way we represent this, what's going to happen is you'll end up with one calcium cation that has a +2 charge overall, and you'll have two chloride anions that have a -1 overall. Okay, so the way you would write the compound, you'd say Ca2+ and two chloride anions are going to form this calcium chloride, CaCl2, and you write this 2 representing there's 2 of these as a subscript when you write the compound overall. Okay, so I don't know how this is sitting with you because I'm not in class with you, but I want to introduce a trick here that may help you with writing compound formulas. And it's known as the switch trick. Some people love it, some people don't, so you don't have to use it, but if you feel like it helps you, great. So I want to look at an example here with, this is a polyatomic ion, this is phosphate. It's got a -3 charge overall. And then this is magnesium, this is a cation with a +2 charge. So if we are going to write a compound, the formula for a compound, and we have cations and anions with different charges, okay? Like their charges aren't the same. Like we have a 3 on our phosphate, a -3, and we have a 2 on our magnesium, a +2. How in the world are we going to figure out how to write the compound overall? Well, the rule here is that our compounds must be neutral, okay? Neutral overall, meaning that the amount of negative charge from all of my anions, like if I had 2 or 3 anions, it must balance out with all the charge from my cations. Okay, so let me explain how this works. The switch trick says you can break it down like this. You're going to look at the charge on this ion being phosphate, and the charge on this ion is a 3. Okay, it's a -3, but we're just going to take that 3, and that's going to tell you, it says the charge on this ion, the 3 there, is the same as the number of the other ion that we will need in the compound. So when we write the compound formula overall, our other ion is magnesium, and the 3 on our phosphate is going to tell us how many magnesiums we need. We're going to need 3 magnesium cations in this compound. All right, just hang on, trust me here. Now let's look at the other side. You can take the charge on magnesium here, which is a 2. It's a +2, but we're going to just take the 2 there. That's going to tell us the number of the other ion that we need. So if we're taking the charge from the cation, that 2 is going to tell us how many anions we need in our compound. Okay, so to get magnesium phosphate, you should end up with 3 magnesiums and 2 phosphates in your compound. So let's see if this matches what we said about things being neutral and our compound being neutral overall. So here's what I'm going to do. If we have 3 magnesiums, that's like saying we have this. I'm going to just write all of them out. We got Mg plus 2, we have another Mg plus 2, and we have another Mg plus 2. We got 3 of them, and each one has a +2 charge. Okay? Now overall, how much positive charge is that? +2, +2, and +2. That's +6 overall, right? Now let's look at phosphate. If we had 2 phosphates in our formula, let me just write those out. Looking at the charge, how much negative charge is that from all of our anions here? That's a -6. -3 and -3 makes -6. So overall, I guess I could highlight it. We've got +6 from our cations, and we've got a sum total of -6 from our anions, and that adds up to 0, right? That's what we mean when we say our compounds must be neutral overall. The total magnitude of positive charge from all the cations has to cancel out with or be the same as the total amount of negative charge from all the anions, all right? And again, if this feels like so foreign to you and you aren't sure what I'm saying, the more you practice these, the more comfortable you'll get with it, and we're going to do more examples together as well. All right, so ionic compounds too must be written as a formula unit. And what does that mean? A formula unit is the simplest ratio between cation and anion with the smallest possible, there's that word, neutral unit. Okay? So like, I could write this. Mg6PO4. And when you do the whole how much positive charge and how much negative charge do you have, it would actually add up to 0. So the amount of positive charge on 6 magnesiums would be the same as the amount of negative charge on 4 phosphates. All that would cancel out to 0. But you know what? It's not the simplest ratio here. 6 and a 4 can simplify to what we originally get, Mg3PO4 2, okay? That is the simplest ratio. We cannot simplify any further, okay? So that's essentially what a formula unit is. All right, so I'm going to go over a few rules that may help clarify some of the things I've been illustrating or walking through on this slide. So these are 3 rules for writing ionic compounds. And the first rule is that you always write the cation first, anion second. Okay, cation first, anion second. So if we have calcium and oxygen, we would want to write that CaO, cation, then anion. We would not want to write it OCa. That's wrong. That's putting the anion first. Okay, so you always write the cation first. Remember, the cations are always the metals, and the anions are typically your non-metals. So it's usually metal before non-metal, if that's an easier way for you to memorize it. You do not include, rule number 2, you do not include the charge on the ions. So if we're going to write calcium oxide, we're going to write it just CaO, no charges. We will not write it Ca2 plus O2 minus. Okay? Because if you know the octet rule, then you know what the charge on those cations and anions are. You don't need to include it when you write the compound. Okay, rule number 3 is particularly about polyatomic ions, and it says use parentheses around the polyatomic ion formula if it has a if it has a subscript. What does that mean? Essentially it means this. If you're going to need more than one polyatomic ion in your formula for your compound, put parentheses around it. It's exactly what you saw us do up here with phosphate, and you probably even wondered, why is she putting parentheses around this? It's because, if I erase all my scribbling up here, when you zoom in, we needed more than one phosphate. This 2 means I've got 2 of everything in here, okay? And so if I need 2 phosphates, and phosphate's a package deal. We don't separate the P and the O's. It's PO4, that is phosphate. And so if I need more than one phosphate, then I put parentheses around my phosphate and I write my subscript outside of that. Okay, so let's look at another example. Let's say that I wanted aluminum hydroxide, and you probably don't know exactly what hydroxide is yet, but go look at the polyatomic chart. Hydroxide is this. It's OH minus. Aluminum is main group 3, so it's going to be Al plus 3. So if I'm going to combine these things and I need a neutral unit overall, this is a plus 3, right? And the charge on hydroxide is a minus 1. We can't change that. That just is the charge on hydroxide. So to get a neutral unit, all we can do is change the number of cations and the number of anions that we have. So it's like you can do this. You can't change the charges, but I could say, well, I could put a number here and say how many cations, how many anions do I need? And then I'll write my formula, okay? So if I've got aluminum with a plus 3 charge, what if we try the switch trick? Remember the switch trick? Take my, let me do black here. take my number here, that'll tell me my subscript for that cation, and then take the number here, and that'll tell me the subscript for that anion. Now let's try to write the compound. So that means I'm going to need 1 aluminum, so Al, and I don't have to write a 1 for my subscript because it's just understood when I wrote Al. And then hydroxide is a polyatomic. Whoops. It's a polyatomic, and I need 3 of them. And my rule here says if I need more than 1, then I need to put it in parentheses and write that number as a subscript. So I'm going to say AlOH 3. Okay, I need 3 hydroxides. If I just wrote it like this, AlOH 3, it would look like this 3 only applies to hydrogen. We want this 3 to multiply everything inside of it by 3. Okay, and then does this give us a neutral unit overall? If I have 1 aluminum with a +3 charge, and then I have 3 hydroxides, negative, -1, -1, this obviously is a +3. The sum total of all these negative charges is -3. And that does cancel to 0 or add up to 0 or give you a neutral compound. Well, that's the wrong one. Compound overall. Okay, hopefully some of this is starting to make a little bit of sense. So this is a really great practice slide. So I'm going to walk through each of these step by step. It'll take some time for sure. So maybe pause this and see if you want to give it a go, and then watch it and see if you got your answer correct. Okay, so we're going to write the compound for the combination of a sodium ion and a chloride ion. All right, so sodium, you might want to have a periodic table handy, by the way, because you probably don't have all these names memorized. But I'm just going to go for it. So sodium is Na, and if you look at a periodic table, it's main group 1, which means it's got 1 valence electron, and when it becomes an ion, it has given away that 1 valence electron, and it is a +1, sodium +1. Chloride is Cl, and as an anion, it's Cl -1. Okay, chlorine has 7 valence electrons. When it gains 1 more to have 8, now it has a -1 charge on it. Okay, so if we're going to write a compound between sodium and chloride, how many sodiums and how many chlorides do we need overall? We have a +1 and a -1. Okay, so do we need 2 sodiums? Do we need 2 chlorides? Well, to get a neutral compound, if we just had 1 each, +1 and -1, that adds up to 0, that or cancels out, or however you want to say it. So we just need 1 each. We just need 1 sodium ion and 1 chloride ion, and so we can just write that compound like this, NaCl. Remember, metal first, non-metal second, or cation first, anion second. And you don't include the charges. So just be sodium chloride. Okay, next one. Iron, here's a transition metal, which is why we're telling you what kind of iron cation. It's an iron +3 cation with Roman numerals, all right? So this would look like this, Fe +3. That is the iron cation, iron +3 cation. And then sulfate, you might not recognize sulfate. It's not an element, it's a polyatomic. So go look at the polyatomic ion chart. You need to write out what sulfate is. Maybe you know it now. Pause this video if you don't. It is SO4 with a -2 charge. Okay, so we want to write a compound that has the iron cation and the sulfate anion. And you can apply the switch trick if you want. Iron has a 3 in its charge, so that means I'm going to need 3 sulfates. And sulfate has a 2 as its charge, so that means I'm going to need 2 irons, all right? So what it would look like is Fe, and then I would write a 2 here because I'm going to need 2 iron cations. And because sulfate is a polyatomic, we need more than 1, and so we're going to have to use parentheses. Remember, that was rule number 3. Use parentheses around a polyatomic if it's going to have a subscript. And the subscript here, a subscript other than 1, I should say. A subscript like 2 or 3 or 4. If you need more than 1, then you got to use parentheses. So I'm going to put it in parentheses and put that 3 outside. Now let's double check. Does this give us a neutral unit overall? Does the amount of positive add up to the amount of negative? Does that cancel to 0? Well, each iron has a +3, right? And we have 2 of them. So it's like saying we have this. Here's my 2 iron +3 cations, all right? And total, this adds up to +6 because each one has a +3. Sulfate, I've got 3 of these. So I've got SO4, 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 each one having a -2. And that adds up to -6 total. And +6 and -6 cancel, add up to 0. So that is a neutral unit overall. Okay? All right. We'll keep going. I'm gonna erase so I have some space here. Sodium ion and bicarbonate. Well, we already have sodium right here. Na plus, or +1. Bicarbonate. What is bicarbonate? This is probably another one you don't recognize the name of. It's not an element. It is a polyatomic ion. Okay. So if you know those or have taken some time to memorize those, it's HCO3 negative. That is the formula for the bicarbonate ion. And we want to write a compound that has sodium as the cation, bicarbonate as the anion. And so I need to look at the charges because I want to write a neutral unit overall. I have a cation with a +1 charge and an anion with a -1 charge. Okay? So am I going to need like 2 sodium cations, or am I going to need 2 or 3 bicarbonate ions? How do you know? You can always try the switch trick. When you do that, you'll see I just need 1 each. Or you could look at the charge and say +1, -1. That already adds up to 0. It already cancels. So just 1 each. So Na, do I need parentheses? Since this is a polyatomic, do I need parentheses? The answer is no, because I don't have an extra subscript that I need to write, like a 2 or 3. I just have 1 bicarbonate. So just by writing bicarbonate, I don't need to add parentheses because I don't need 2 bicarbonates or 3 bicarbonates. I don't need more than 1 polyatomic. So NaHCO3, that is sodium bicarbonate. And then the ammonium ion and the phosphate ion. So ammonium, this is another polyatomic. It's one of the few cation polyatomic ions. Most of them are anions. Most of the polyatomics have a negative charge. But ammonium is unique because it's NH4 and it has a positive charge on it. And then phosphate, we looked at earlier when I first introduced the switch trick. We had phosphate on the slide, and that was PO4 with a -3 charge. Okay, so again, you may not have all these memorized right now watching this video, but take some time over the weekend to know your polyatomics, and that will really help you. Now, our cation has a +1, anion has a -3, so how many of each, how many cations and how many anions do I need to write a neutral compound overall? Let's just do the switch trick. I'm going to need 1, well, I'll write it like this, 1 phosphate, and I'm going to need 3 ammoniums. Okay, now because ammonium is a polyatomic, and I'm going to need more than 1, I'm going to put it in parentheses. So it'll be NH4, and we said I need 3 of them, and then I need 1 phosphate, so I don't need parentheses on the phosphate since I just need 1, so I'll just write it. Now let's double check. We've got 3 ammoniums. Each one is a +1 charge, so I'm not going to write out the full formula for the compound, but I'll write out all 3 charges, like this. So total, that gives me +3, right? And phosphate, I just have 1 of them, which is a -3, and +3 and -3, that gives us a neutral unit. So this is the correct formula, NH4 in parentheses 3, PO4. Okay, so this is all of a sudden a lot of rules being put together, so that can make the naming part challenging. But you'll get a lot of practice on homework 3. Don't worry. I don't have a poll question on this. Sorry, since it's not live lecture. Okay, here's more practice. I'm just going to do like 1 or 2 and maybe let you do a few on your own. Name the following ions. Okay, so here we're kind of working backwards. You're given the formula for the ion, or the symbol for the ion, and now I want you to name it. So go look at a periodic table, which you will have for the exam, and you'll see that Cu is copper. you will also see that copper is a transition metal. So I can't just say the copper ion. That's how you name main group cations. This is a transition metal cation. So I've got to say the copper 2 ion. All right. And then let's do number 4. S minus 2. So this is sulfur, but because it's an anion, we have the IDE ending on the name, remember? So this becomes this is the sulfide. There's that IDE ending, sulfide ion. Okay. Awesome. And then I'll do one of these below. Write the symbols for the following ions. So the silver 1 ion, if you go look at periodic table, silver is right there, Ag. And so we would just write Ag, and we'll indicate the charge, which is given by the Roman numeral here, with a plus sign. You could write plus or +1. Let's go ahead and do B as well. I see Roman numerals, so that means it's got to be a transition metal. So I'll come over here. Iron on the periodic table is, it's Fe. So I'll write Fe, and the charge is a +2. That's what those Roman numerals is indicating. How do I know it's +2 and not -2? I know that because it's a metal, and metals only form cations, okay? Metals form cations. Okay, non-metals form, sorry for my handwriting, anions. Okay. You can also look at the name ending. When you see that IDE ending, you know you're dealing with an anion. Okay, that's going to be a negatively charged ion. But if you don't see IDE, it's probably a cation. Okay. This is a lot of practice, a lot more practice, so I'm going to skip over this slide because I think already this video is getting lengthy, and I'm going to go to this slide. But it would be great for you to practice this if you want. It's just writing more formulas from ion names, kind of like what we did earlier. Okay, so properties of ionic solids. This is going to be the last slide in our video here. We've been talking about ionic compounds, ions, cations, anions. Now I just want you to know some general properties about these types of compounds. Ionic compounds form what we call crystalline solids. Okay, so we don't call ionic compounds molecules. All right, we call them crystalline solids. All right, and some ionic compounds dissolve in water to form solutions that are good conductors of electricity. Okay, because you got all these little charges in your solution, and charges can weakly, sometimes strongly, conduct electricity in solution, only when they're dissolved in solution, okay? This just shows you an example. I guess I should have explained this when I'm using the word crystalline. Obviously, the root word of the word crystalline is the word crystal, and we know crystals are like very ordered, structured things. And so the reason this happens, the reason they're so like ordered and nicely arranged, is because, let's look at sodium and chlorine here, this purple sphere and then the green one. All the positive spheres are going to want to surround themselves with as many negative spheres as possible because there's an electrical attraction there, right? Positive and negative attract. And so all these little blue, sorry, what did I just say? Purple. It's late, guys. All these little purple spheres are going to surround themselves with as many greens as they can because they're attracted to each other. And all the greens are going to surround themselves, if I focus on a green here, are going to surround themselves with as many purples as they can, again, because there's electrical attraction. And when they do that, they automatically order themselves, okay? So you get this nice ordered arrangement. That's why when you, like, cut a crystal or a diamond or something, it doesn't just, like, shatter into a million pieces. It cuts along these nice ridges, and you get these nice, like, diamond shapes because they're crystalline solids, okay? Okay, rule number 3, or property number 3, I should say, is ionic compounds have very high melting points and boiling points, okay? That's because all of these little attractions between our positive and negative cations and anions, they're like holding each other together really tightly because they're attracted to each other, versus atoms that are not held together with charges, which is what we're going to get to in chapter 4. Okay, so because there's all these positive and negative, full-on positive negative charges and these attractive forces holding all these cations and anions together, it's really, really hard to like break these or dissolve these molecules apart or these atoms apart. I shouldn't say molecules, right? It's hard to pull these cations and anions apart, and therefore it takes a lot of heat and a lot of energy to melt them and to boil them or to turn them into liquids and gases. Okay, lastly, ionic solids shatter when forcefully broken. Okay, glass would be an example there, but they shatter because, again, they are these ordered crystalline things, and so when they break, they'll typically like break along a line of charges or along a ridge or an edge. And so, anyways, that's all the properties I'm going to talk about with ionic solids. I don't have that, so no more practice problems here. That's the end of chapter 3. So definitely practice naming all those compounds. There's a lot of homework problems that have you name compounds and name, I don't know if you name ions, but anyways, please email me with your questions. I hope you wrote those down as you went, and I hope this was helpful.